We've been talking about this idea of current, but let's actually try to define what it is. So a common thing to do is to talk about what we would refer to as the electron current. And so this is the idea that you have some piece of material, let's say a wire, like a tube like this. And what you're trying to do is basically decide what's the number of electrons that pass by a specific location per unit time. That's really all it is. It's counting the number of electrons that pass by per unit time. We often call that electron current or we refer to it with this little I. And it's literally counting the number of electrons that pass a given location per unit time. So it has units of essentially electrons per second. Okay? Now, the other thing that's actually interesting about this is that it is related to measurements of the electrons themselves. That is, if you have some electron that's moving along this way, and it has some average velocity, and it's in a piece of material that has an electron density, a number density of available charge movers with a cross-sectional area of A, this electron current is also the number density, the available number of charge carriers, the number of electrons that are available to move per unit volume, times the cross-sectional area, times the average velocity. So this actually relates the micro measure of electron current and number density to macro measures like how big is the wire or how fat is the wire. Now these two things actually match up pretty easily because if you look at the electron current, like I said, it's the number of electrons per second. So this number density is the number of electrons per meter cubed. This cross-sectional area is meters square, and the average drift speed of these electrons is in meters per second. So all this stuff cancels out, all the meters cancel, and give you something that's in electrons per second. So they seem like they're related. Now, a couple of quick things to say about this is that most of the kinds of pieces of material we're going to deal with that have electrons that are moving have a very high electron density, something like 10 to the 28 electrons per meter cubed. So this is considered a high density. This would be something like copper. The other thing is that the average velocity, the average drift velocity of these electrons is very low. It turns out to be something like 10 to the minus 4 or 10 to the minus 5 meters per second. That's the drift speed. And so there's some interesting questions there about if these electrons move so slowly, why is it that when you turn on the light switch, the light comes on immediately? That's something to think about. Now this electron current is related to the thing that we would call the conventional current. This is the thing that you can actually measure with a multimeter or an ammeter, something that you're actually using in the laboratory. And it's a very, very straightforward relationship. The total conventional current is going to be equal to the charge of the charge carrier times the electron current. Now these charge carriers can be positive or negative. They typically tend to be electrons, so they typically tend to be negative charges. The other thing that we have to pay attention to is that this conventional current for negative charges goes in the opposite direction of the electron current. The electrons actually move this way, but the conventional current that we measure is measured in the direction that positive charges move. That confusion is brought to you by Benjamin Franklin. So this Q is typically for us going to be something like 1.6 times 10 to the minus 19 coulombs, meaning that the units of the units of conventional current are in coulombs per second, which is also known as an amp. So the relationships that we've shown here discuss electron currents. So if you're actually watching the charges themselves move past a certain area, that's the thing that we're focused on, is the electron current. It's not the thing that we measure, which is the conventional current that's actually measured with multimeters. But they're related through this fairly simple relationship here.